Hello? Yes. Okay, thank you very much. So thanks for the organizers. Thanks to the organizers. I will speak about aspects of calorimetry. If I would have chalk, it would be. So calorimetry, I guess you know from elementary physics and chemistry. It's, I hope, still a well-respected topic in, well, starting with equilibrium thermodynamics, of course, where one of the main players is the heat capacity, or the specific heat, molar heat, things like that. And maybe let me remind you what is its first meaning. So we will denote it with the letter C of capacity. There are, in fact, many capacities, depending on what constraints you have. But it's, you can understand it as a kind of inertia against temperature changes. So the relation that you all know is that you will give some amount of heat, and then the temperature, if you give the heat to the system, maybe the temperature will change. So this is the change of temperature. And the relation that relates that heat turning into a change in temperature or vice versa, that is the heat capacity, right? So in that sense, you can find in the books and in internet values of the heat capacity depending on the substance. So these tables would go like that, like you write something like the heat capacity here, then say, okay, it depends a bit on whether it's constant volume or constant pressure. I'm not going to speak about that. And then you get, say, so many joules per gram, for example, per degree Celsius. Maybe you want to have it at a certain temperature, say 25. And then if you have water, that would be like 4 or something like that, which is very high. And then when you are like gold, it's very low. If you have like wood, it depends on whether it has a lot of moisture in it or not, but it would be varying between 1.3 and 1.9 or something like that. So this is the information you get. These are material constants, and you can also get other things. You can also find drawings like that. So then you draw here on the horizontal axis the temperature, and here you put, for example, let me take the heat capacity at a constant volume. And I don't know what substance you like most, but for example, for solids, it would be, suppose I could say, if I divide by the Debye temperature and I divide by 3R, where this is the universal gas constant, at high temperature it goes to 1, and then it goes to 0 at 0 temperature, and here the interesting thing is that it goes like T to the cube, for example, for copper, aluminum, and all of these things, right? This is what we learn in school. And that somehow is a mixture of thermodynamic insights and statistical mechanical insights, where this, of course, is the important relation, and where it's on the level of the first law of thermodynamics, truly, right? Where you look at the change in energy as corresponding to it, heat and work which is done on the system. That's all what you have to know. And if you really care for great sophistication, you can even try to understand how the heat capacity is related to the entropy by saying that, by applying the first part of Clausius' heat theorem, by saying that there is an exact differential thermodynamic entropy, which is related to this heat. So these are basically for equilibrium thermodynamics, the main thing. But then you really need to start doing statistical mechanics to interpret this heat capacity, and you learn a great thing. Maybe I should remind you, or maybe I should not remind you, but a lot of our textbooks and our courses are emphasizing that the revolution in quantum mechanics was steered, of course, by experimental results, and were steered in particular by black body radiation, hydrogen spectra, photoelectric effect. But in fact, in reality, the revolution was much inspired in the early days by heat capacity measurements. So for example, here, this Dulong-de-Petit law at high temperature, it was absolutely a mystery why it was clear in the middle already in the 19th century why you had it going down to zero, actually. So Maxwell, who was one of the pioneers in developing the kinetic theory of gases, said it's a wonderful theory, but there is one thing that we absolutely don't understand, that's specific heats. The same happened with Gibbs, with Jaynes, and that was also the main topic, actually, in the 1911 Solvay conference, where Einstein proposed to apply the ideas of Planck applied to black body radiation to the specific heat of solids to understand, indeed, why you have the low temperature behavior that you see. And applying in that way, for the first time, the quantum hypothesis to, well, condensed matter theory. And in fact, this kind of law was already in 1912 there by Peter de Baeye. So that's the signature, you could say, of quantum mechanics that helped, where, of course, statistical mechanics was giving you expressions for the average energy of a photon gas or of another kind of quantum harmonic oscillators, and then at constant volume, the heat capacity, as you remember, is just the temperature derivative of the equilibrium energy, right? And that's how people were able to then compute these low temperature heat capacities. And at that time also got established this very interesting fact that not always, but sometimes and often, for reasons that one understands, one has a third law of thermodynamics, namely where, more or less equivalently, the heat capacity goes to zero at zero temperature and thereby sets the full scenery for everything which is low temperature physics and chemistry, in the sense that it puts up an absolute constraint to all possible processes, physics unattainability at the zero temperature state, etc., etc. So these are signatures of statistical mechanics and signatures, so in other words, signatures of fluctuations and signatures of quantum mechanics that you got in heat capacity. So this talk I would like to see, I mean, in accordance with the title of this conference, whether you could also have signatures of non-equilibrium in heat capacity. So what is the experiment I propose then? Well, let us look at wood. Maybe I will take advantage of the blackboards. Why are you standing up? I mean, if you want, you can. Okay, so I just say we will have about wood. So we can, of course, start by taking a block of wood. Okay, nice piece of wood. And that would be the heat capacity, please. Yes.
I have a question about the interpretation of the heat capacity in terms of the number of degrees of freedom.
Yes.
I mean, in classical statistical mechanics, equipartition tells that the heat capacity is proportional to the number of degrees of freedom in the system. And I have a curiosity question. In quantum mechanics, the heat capacity goes to zero, like you are showing here. Can one say that can one infer that actually the numbers of degrees of freedom as you go down in temperature also goes to zero somehow?
Okay, so we have...
Because they are quantized or something like that?
The answer is of course, but one can be a little bit more precise. Instead of, say, counting the degrees of freedom, the better word here is to understand degeneracy. Right? So you have to understand what is called residual entropy and ground state degeneracy. So the third law of I'm not going to lecture you, right? But the third law of thermodynamics is not like the first and the second law in the sense that it is not intrinsic to the formalism of thermodynamics. There are exceptions. You know, like Pauling in 1936 already spoke about ice and residual entropy, and there are spin ice, which are very important today, and they do have residual entropy, so the third law is not always satisfied. But indeed, for many systems, one can show that entropy goes to zero at zero temperature. In equilibrium, that is in fact completely related to the interpretation of entropy in the Boltzmann sense as the logarithm of the availability of the degeneracy, and can be reduced to that. So for example, the Planck version of the Nernst postulate also was that for a pure crystal, the entropy goes to zero, because the entropy is measuring the degeneracy, the logarithm of 1 goes to 0, in other words. So there is this interpretation, and it has been studied. But I will come back to it and how that changes in non-equilibrium, actually.
Okay. Okay, thank you.
So let's go back to wood. So we have with wood, we measure the heat capacity, and we get such numbers, 1,300, 1,500 joule per kilogram if you want to increase per degree of freedom. But now let us be having the dream like Geppetto used to have. And so we kind of want to call the fairy to come to put life in it. And so at the end of, after you slept well, and the blue fairy has been going, then you would see maybe something like that. And wait, and then and so the question is, after all that magic, what is the heat capacity of Pinocchio? In other words, in what sense can we still speak about heat capacity as a material constant, or something that depends on a number of material aspects and volume and what have you? But in what sense does it also matter whether there is a kind of biological functioning or activity? And the inverse question, can we learn by measuring the heat capacity? Can we infer, that's a nice word to do, can we infer aspects that have to do with the structure of the material, but also its functioning? After all, I mean, as you know, that from heat capacity, you can, it's a spectrometry, you know? It's measuring the spectrum and the degeneracies, as Felix was also mentioning. So you would like to understand, what does the non-equilibrium heat capacity add to that spectrometry to understand the spectrum of the material? Is it okay? You understand the motivation and the... So for example, hydrogen, if you go 100,000, I mean, you know, there is this transition between the translation degrees of freedom, rotation degrees of freedom, vibration. You all learn that in school, right? And that happens at certain temperature when you get these excited degrees of freedom. Okay, so these are the questions, but more than just spectrum, is there more to be learned from non-equilibrium heat capacities? So we put here the non in front. And the first question is, what do we mean by non-equilibrium heat capacity? Okay, so I will first explain that in a more conceptual way, but not in the way how you would actually measure it. But just to explain the concept is maybe even more important for today than how you measure it. Okay, so let us consider one of the great progress that humanity has been made over the last years, and that is how you make hot water. So you take, like you want to make tea for I'm sorry that the blackboard is not very good. So you have some pot of water, say. Oh. So water, say. Water. Okay, and what you do, you put a resistor in it. No, that's not a resistor, right? So let me put a resistor in it. And then I attach it to a battery, if you can all see it. And if I have some voltage, I'm doing work, the battery is doing work. And well, you know what you get? You get what is called Joule heating. So you're doing work, and that is turned into heat, and that heat has a red color. And that makes the temperature, that will increase the temperature of the water, right? And water is very hard to warm up, so you'll have to wait a little bit while you smoke a cigarette, and then you get hot water. Okay, by the way, we learned also in the last talk that you could also use an aqueous watch for that, and then you would have to wait at least 2.5 days before you could get a cup of hot water. Okay. But now suppose we do something extravagant, namely we want to make like a hot water for many guests. So we will have a lot of water. Can you imagine a lot of water? So we have a lot of water, so much water, in fact, that and so many fish that also swim in the water that it's quite diffusing this thing, so that we have a fixed temperature. So we have here a lot of water at a fixed temperature. That doesn't stop the Joule heating, right? So there is still power being dissipated in the water. But now we can speak at the power as a function of temperature, right? So what we then have is the following thing that really is at the heart of thermodynamics, whether it's equilibrium or non-equilibrium, and that is that you would like to connect one non-equilibrium steady state, which is this whole thing here, this resistor. We would like to connect it to another non-equilibrium steady state and compare the transition, the transformation between two non-equilibrium steady states. So let me do that by the following figure. But maybe orange will be better. So this is now the arrow, the time is in the horizontal axis, and here I have the power, this kind of red power here, right? This Joule heating per unit time. So let's say that before time zero, so here is time zero, we have on average a certain dissipated power, and it's strictly positive. That is the situation that we have, just entropy production, if you wish, or power dissipated to our environment. Let me speak about one heat bath for the moment. Okay, but now, of course, there are fluctuations. It's nothing really constant, so it may be that, in fact, at time zero, you are not exactly having a state which is corresponding to the mean. For smaller systems, that will be very strange, that the mean would be relevant for you. But there will be a certain fluctuations around it, fine. But then if you, say, do something to your system, and let me do something specific because of lack of time, I will simply imagine that I have my water to be changed from a temperature T to a temperature which is slightly different. So I, for example, add dT to my temperature, okay? Then, if I wait long enough, I believe I could imagine that I get again some average power which is dissipated, but maybe different, maybe bigger, maybe higher, smaller, I don't care. But there will be a new dissipated power that is going to be happening, right? Okay, but what happens between here and here? Well, there is something going to happen, probably. So the figure, it's caricature, no? It's conceptually trying to understand the notion of non-equilibrium heat capacity. So there probably will be, some kind of a transition where I'm drawing here a curve of the power. And that will happen also in equilibrium. So in equilibrium, the analog of this thing would be that you have zero power before, zero power afterwards, but you have some bump in between, right? And the equilibrium heat capacity would be just this area multiplied with dT, right? So what is the non-equilibrium heat capacity? Well, the non-equilibrium heat capacity is you take this area, I can make an area here, that's the heat capacity times dT, right? So that's the very conceptually simple and straightforward extension of the notion of an equilibrium heat capacity to a non-equilibrium heat capacity, simply by taking the excess heat instead of the straight heat. The point is, of course, in non-equilibrium, aqueous watches and resistors, they already give heat to your water, but that is not the interesting part. What is interesting is that you really look at the excess as you change from one non-equilibrium regime to another non-equilibrium regime. And that excess is proportional to dD, and the constant of proportionality, that's what you call the non-equilibrium heat capacity. Obviously, it reduces to the equilibrium heat capacity when you're in equilibrium, but it is operationally also possible. It's not just some invention in the sense that it is quite natural, has an operational meaning. I'm not going to give too many mathematical formulas unless you insist. But it is, of course, you can propose other non-equilibrium heat capacities, but that one, yes, please.
This power is the internal power, not the external power, right?
No, this is what your, that is the heat, which is the heat flux.
Okay, so it's the internal power. Because external power is The
I
current
don't know about
multiply.
internal and external.
Well, the power that you supply is the current.
Oh, the battery, you mean?
Yeah.
No, the battery, okay, this is here in this example, you have a mechanical reservoir and you have a heat bath. I'm speaking about the thermal bath, the heat bath at a certain temperature where there is dissipation. I'm not looking at dissipation in the battery.
Yes, it is internal power. Okay.
So just a question about the kind of non-equilibrium systems you have in mind. So
I have all non-equilibrium systems in mind, but here I have in mind the steady state. It can be a time-dependent one.
So let me get to the point. I think, so here you have to assume that the temperature is well-defined and homogeneous in space.
No.
So then what is...
You see, the non-equilibrium system is here. That's the weakly coupled to the environment, and it's the environment, which is an equilibrium reservoir, which is at temperature T.
So it's always at equilibrium.
I'm always speaking, you see, non-equilibrium statistical mechanics and non-equilibrium thermodynamics cannot do without equilibrium. Well,
yeah,
maybe.
yeah.
But here in particular, heat capacity is, you are measuring the power dissipated, the heat here, with a certain temperature, and for heat capacity I need it. I can imagine much more complicated systems, and of course you can consider them, where in fact this is not immediately true, that you first couple to a tissue, which is full of molecular motors, and that one is then sitting in a big water reservoir, and that water reservoir is sitting in a big air reservoir. All of that I can also imagine, but I don't want to speak about it in such complicated ways. So temperature is not a temperature of my resistor. You could say that, but I don't need to do that. The temperature is the one of the heat bath, the equilibrium reservoir, one of the equilibrium reservoirs. You see, you can imagine easily that this heat capacity becomes a matrix. Why it becomes a matrix? Because I can have different heat reservoirs, and I can change one temperature here and see what happens to the heat flux there. Right? So you can have all kinds, you broaden somehow the concept because you have more reservoirs, more. But I need at some moment, when speaking about heat capacity, by the nature of thermal response, I need somewhere to speak about temperature, and it's of an equilibrium system.
Yeah, okay.
Okay. All right, so where was I? Yeah, so that's the conceptual definition of heat capacity.
Question.
Please.
On the picture in the middle, if it's steady state, why temperature changes?
Why do you think?
I have no idea.
Okay. Because I changed it. No, the temperature is the temperature of the reservoir. So I change it. The resistor is in a steady state, but at a certain temperature, and then I change the temperature, and then it's transient. You go from one to the other, just like in equilibrium. Right? It's just like in equilibrium. Is it clear? Yeah.
So when you change the temperature, the whole system does a whole excursion, right? But the temperature outside is still the same. So so what you add, it would be like the excursion is not in the temperature, right? It's only a flow of an excess flow of heat.
I mean, you're heating up the room, right?
Okay, yes.
Okay,
so if the temperature change,
suppose we change the temperature of the room.
Okay.
You will still be heating up the room.
Okay, and then you heat
more
the room. You heat more the room as if compared if I was non.
I'm not saying that it could be less or more. So now it's like, I don't know, 20 degrees here or so, Celsius. So you're heating up the room.
Yes.
For which we thank you. And then now we change it to 25 and you have another dissipated power. But there will probably be a transient regime where you go from one steady state to another state. You have to adjust yourself, right? And while you adjust yourself, that is the non-equilibrium heat capacity which will enter.
Okay, and I will heat the environment more or less than if I was in an equilibrium system?
Well, that's a good question. That's exactly what we, if one way or the other, right? And we will get some information from there. Okay. Yeah, so I was saying that this is the conceptual way of doing things, because obviously, well, obviously it's not completely obvious, but in a non-equilibrium experiment, you can change the temperature, but you see this is a steady state thing. I mean, you will have to worry when you actually reach this, and there will be all kinds of fluctuations, so this will be not so easy to do that. But fortunately, there is another way to do that, and which is basically AC calorimetry. So what you're doing is, instead of changing the temperature suddenly, you're in fact having a non-equilibrium steady state with a modulated temperature, and then you can prove, as we do, that this same non-equilibrium heat capacity is obtained as the out-of-phase component for the heat flux, which is now also time-dependent, going into the reservoir. Okay, this is another way. If you want to do the mathematics correctly, which is fun and nice, you have to develop the so-called theory of quasi-static transformations for non-equilibrium thermodynamics. So this little TT here, which I'm writing, is just an abbreviation of something which is more pleasant, which is quasi-static transformations. And that also then gives you formulas for these non-equilibrium heat capacities, which are extensions of these formulas, like the derivative of the energy with respect to the temperature. In non-equilibrium, that's no longer true, right? Non-equilibrium heat capacity is not a non-equilibrium expectation of an energy with respect to temperature. So you get some new formalism which comes with the dish automatically. But okay, these are things that everyone can do, or you can look it up. There is a paper in Journal of Chemical Physics which is appearing right now, and which is a collaboration with Karl Netochny and Maes da Ben, I guess. Da. Da Ben, da. Lu. She will kill me, but it's okay. I mean, I don't know exactly whether it's something. We don't have a first author in our business. He's a very precise and okay, where was I? Okay, so yada, 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 you get these kind of mathematical formulations. So let me now go to what are the real questions that, after you have developed this theory, what are the real questions you would like to understand and that we partially understood. So let me try to make a list of these questions very quickly. Do I have time? So one of the questions is, of course, well, let me just randomly say that what do you learn from the heat capacity, right? So for example, is it thermodynamic information? What kind of thermodynamic information? But maybe you also get kinetic information, which you are not accessible for equilibrium. So for example, you have a two-level system. You have a heat capacity, but the heat capacity for a two-level system, if you know, a two-level system is 2 levels of energy. And if you do the heat capacity of a two-level system in temperature, you get something like that, okay? That's the heat capacity of a two-level system. What you learn is where the peak is, and this peak is basically telling you what is the energy difference. So you can use calorimetry to understand the energy difference of the two-level system, and mutatis mutandis for a multi-level system. And you see this Schottky anomaly, and you can understand, of course, why. Okay, so that is information. But for example, suppose that your two-level system has a barrier. So think about a two-level system which is realized in such a double well potential. Then you see this energy difference is just this energy difference. But how do you measure the kinetic barrier? That's not in the heat capacity. So what I say, or what I claim, and what maybe I will show you, is that if you turn this two-level system non-equilibrium by making it into a switch, basically, or molecular switch or something, then you will be able to measure this kinetic barrier, which was there also in equilibrium, but now thanks to the non-equilibrium heat capacity, you will actually see it. Other information that you may have is that kinetic information, which you do not have any equivalent in equilibrium, is that, you know, in non-equilibrium systems, you can have population inversion. Right? It may be that the Boltzmann distribution is frenetically so changed that the high energy levels are the most occupied levels at low temperature. So that you have to give energy to go down in energy. Right? So that leads to negative heat capacities. So by discovering negative stable system, a stable non-equilibrium system with negative heat capacity will tell you something about this population inversion. Right? So these are what I would say a first thing that you will discover the amount of activity, of driving, of population inversion, of barriers, kinetic barriers, to some extent at least, by heat capacity measurements beyond the purely spectrometric information. Yes, please.
This measurement of non-equilibrium heat capacity in this two-state model, you go from upper level
That's an equilibrium system.
Yeah, from upper level to lower level, you will get one non-equilibrium thermodynamic. But if you go opposite way, from level 2 to 1, will it be the same curve?
No, sorry.
No, it will be the same
so
thing.
I'm talking about the steady state of a
Right.
two-level system, where
Right.
you have a certain occupation, typically at low temperature in the lowest state and a bit in the higher state, right?
So it doesn't matter where you start, right? It will be the
No,
same.
I'm talking about the stationary, i.e.
Okay.
steady state two-level system. I measured the heat capacity. That's the typical Schottky peak that you have for a two-level system with the peak around the, whatever, KT, whatever the corresponding to this.
Okay, thanks.
To this energy.
Sorry.
Maybe I will give you more examples if you wish. But where was I? So this is the first kind of bulk thing that you would like to understand in how to get information which goes beyond equilibrium and which is also really signaling life. So a second thing you would like to know is whether there are some general features that that are law-like, so law-like behavior. And so the thing that you want to understand, for example, which I here, so think of this as a heat capacity. So this is not strange. We understand why this goes to zero at zero temperature. The question is it also true for non-equilibrium heat capacities that it goes to zero? So is there an extension of the third law of thermodynamics to non-equilibrium in the sense that the Nernst postulate is verified when it has to be verified? The answer is yes, there is such a thing. So there is an extended third law. But interestingly, it requires more than the equilibrium version. As Felix was mentioning, for equilibrium thermodynamics to have a Nernst postulate verified, you go with non-degeneracy. It's a static condition, right? If you go non-equilibrium, the intuition, in fact, changes in an interesting way. Because perhaps some of us has the intuition that at zero temperature, the world freezes. It kind of goes well with zero temperature, right? The world freezes and kind of no longer moves. Well, exactly for non-equilibrium heat capacity to go to zero at zero temperature, you need to have residual dynamical activity. So, as always, it is the frenzy which is going to help you here. It must be there, or you will not have a zero law. Not a zero law, a Nernst law. So, in other words, you can have a zero temperature phase transition, which signals jamming at low temperature. So if you kind of stand still, if the energy dissipation is not violent enough, then you will in fact have no third law, and it is only when you have a lot of quantum motion, residing quantum motion, the kind of quantum fluctuation it's sometimes called. If you have enough of that, only then you will have a third law, yeah.
So sorry, maybe this is very naive question. So there is one way to be in equilibrium and many ways to be in non-equilibrium. So I guess
I don't agree. There are many ways to be in equilibrium and few ways to be in non-equilibrium.
Okay, so I would like to know about this. So these general features. So I would expect that something depends. This phenomenology also depends on how you drive the system in the non-equilibrium steady state.
That's absolutely true.
Whether these general features refer to the system itself, I mean the height of the barrier, which is a property of the system, or to the way in which you are driving the system.
So that's, thank you for your question. That's an interesting question, but it goes in the direction of what I was trying to say in my first point. Namely, you get non-thermodynamic information. You get kinetic information, and this splits in two things. The one that is already there in equilibrium and that becomes visible, but also the one that you use to make it non-equilibrium. Of course, within certain limits, a lot of these things require, heat capacity is not something arbitrary, right? So it requires that the ability to have a quasi-static transformation, which is certainly much helped by recoupling situations. So it's not something which is wildly available. I mean, that's maybe not so strange. But indeed, in the cases where it applies or where it makes sense, you will see from heat capacities differences in the way you're driving. So maybe I can, an example. Well, I don't know whether, suppose I take maybe a stupid example. Take again my two-level system, right? So here is my two-level system. So I make it into a switch. I try the switch in the following way, that I have it switched at a rate alpha between, I guess, this thing. Right? So I switch randomly the two-level system between these two. So that's an extra parameter now that will be there. Well, you will see it in the heat capacity, obviously. Right? Now, suppose I do something different to switch it, you will see it in the heat capacity. So in other words, from the heat capacity, you will be getting hints about how it gets in non-equilibrium, what kind of non-equilibrium. So that is what I meant also by this general term, kinetic information. Yeah. Okay. I think I'm finished, or not? Did I, wait a second. So there was this third law here. Oh, this is general features. This is this third law. And then, okay, a general feature is the understanding the negativity of the heat capacity, which is kind of interesting signal for aspects such as population inversion. And in fact, for those who like more foundational aspects, let me stop with just this remark. You know that in equilibrium, I have to say more things actually, but I have no time probably. How much time do I have? Okay, so let me say two things. So first of all, in equilibrium, you remember that, say, if I have the heat capacity at constant volume, it is related to the variance of the energy. Right, so it is a typical fluctuation-dissipation relation. You have a thermal response, which is expressed in terms of a fluctuation of the energy, and that's also why it is positive in the canonical ensemble. If you go to non-equilibrium, you show that this heat capacity is no longer the variance of an energy. Actually, there are beta squares here or something. But it is a covariance, and it's a covariance between something which I will just very vaguely call the heat or the excess heat and the amount of degeneracy, blah, blah. So I'm sorry for being a bit descriptive here, but I would like to refer to the following. The Clausius entropy is directly related to heat, right? Miraculously, in equilibrium, this Clausius entropy is exactly related to a completely different entropy, which is the Boltzmann entropy, which is a configurational entropy measuring degeneracy. I mean, this should be a one-semester course on equilibrium statistical mechanics just to explain that fact, right? That the Clausius entropy is equal to the Boltzmann entropy. So if you have a covariance like that in equilibrium, it reduces to something like that because they are the same. In non-equilibrium, the ways of Clausius and Boltzmann separate. And in fact, to such an extent that the correlation, the covariance between Clausius and Boltzmann can become negative. And that's exactly what you see in negative non-equilibrium heat capacities. how the Clausius and the Boltzmann separate, sometimes to such an extent that it's no longer true that heat is related to the spectrometry of spectroscopic aspects. That's the first thing I want to say. Second thing I wanted to say is the following. Of course, this notion of thermal response is just response by changing the temperature. I can do experiments with the same setup with changing other parameters. So then I come into this broader realm of non-equilibrium response theory, right? You can do it quasi-static or not quasi-statics. You have more possibilities, of course, to discuss response theory. But what I hope I would like to emphasize is that when you're doing non-equilibrium response theory, it's not only Clausius nor Boltzmann entropies that matter, or other types of H functionals or Onsager dissipation functions. All of these dissipative things have only one little role in this response theory. What really becomes important as a second ingredient in such a response theory for non-equilibrium systems is a dynamical activity, which I emphasized also for the validity of the third law, meaning that there is time-symmetric activity. There are not just currents which are antisymmetric, or at least giving an arrow of time, but somehow paradoxically, in non-equilibrium, the time-symmetric aspects become relevant, and they enter explicitly in these responses. And that's also why, as a specific case, for non-equilibrium heat capacity, it becomes a phrenometer. So in other words, the thing that you do when you want to go to Pinocchio is that this calorimetry, which I was trying to write here, becomes in the end a phrenometry, by which I want to thank you.
Thank you. We can take a couple of questions. Students first.
Sir, thank you for this talk here.
Oh, sorry.
So, did I understand it correctly that for non-equilibrium systems, the third law is violated?
No.
Okay, so...
So I wanted to say that so in equilibrium it is not always true, and in non-equilibrium it's also not true. Sometimes not true. In equilibrium it is sometimes not true because there is residual entropy, so not enough non-degeneracy. In non-equilibrium there is a second reason why it can fail, namely not enough dynamical activity at zero temperature.
Okay, so
that
means it's not it will not be true all the time.
In equilibrium, it's also not true all the time. But what is more interesting is that we understand when and why it is not true.
Okay, and can this be generalized for all other laws of thermodynamics?
Well, no, as I was saying, third law is a bit of a specific case in the sense that, first law is basically conservation of energy.
Yes.
There is a bit of a problem if you go to general relativity with the first law, because you probably know that a local energy density in general relativity is a bit difficult to define. So there are some problems with the first law. Second law is much more general. It's almost like a meta law. Wherever you do, there must be a second law. Third law is not intrinsic to mechanics or statistical mechanics. It's a consequence in many cases, but it's more like a property than it is a law.
Okay, I understand. Thank you.
The fourth law, we are not sure.
So I wanted to know the scale of this in real living systems. I imagine that in a real living system you have two-component capacity, one that is equilibrium, basically water, right? And another extra proportion of this non-equilibrium component. I wanted to know what we are talking about. It's like 1%, 20%?
Well, I would hope a lot of percent that you're quite different from just a bag of water, also for heat capacity, but I don't know really.
It has not been measured.
I hope I did not give you the impression that I know much about living systems and their heat capacity. I would just have a hope that this would give another window of thinking about heat capacity as not just a material constant, but also related to functioning, activity, and things like that. But somehow you could have the intuition that if you take Pinocchio afterwards or before, that he has the same heat capacity, the conclusion of the talk is no. You will see the appearance of the blue fairy somehow.
Other questions? Also from the audience.
There is a question there.
I will ask.
But there is also another question up in heaven.
Hello. Hi. Wonderful talk. Finally, I want to know, will the heat capacity of Pinocchio be lower than the wood or would be higher than the wood?
Well, typically what you have is that neither of the two, but it depends on the temperature. So, for example, it will be the following. So here is temperature, here is the heat capacity of Pinocchio. So the heat capacity of Pinocchio when before, just Geppetto stable, will be something like that. And after that, the blue fairy, do you know the blue fairy?
Okay, heard about it.
That's why I use blue. It will be like that. Okay? So here it is a magnificent increase of heat capacity at a temperature of about 250 below zero. And then it will be, but it will be lower at higher temperature.
Can I consider that as a signature of life, or is it?
Of course, you will. But so you have to be careful, no, with this experiment, because you could kill Pinocchio.
Okay, we are out of time. Okay, one last question.
Look, now the questions come.
Oh, okay.
So you spoke about measuring time symmetric and time asymmetric contributions in non-equilibrium. So in AC calorimetry, these would be in phase and out of phase?
No, this is completely different. So the measurement of heat capacity is the out-of-phase component in the modulated heat flux. But this non-equilibrium heat capacity contains information both about dissipation and frenzy.
Hi, here. I enjoyed very much your talk, thanks. Going to the analogy of Pinocchio, if you consider a system that self-organizes, I'm thinking in a virus, that is all separated, the component, and then eventually inside the cell it picks the right form. Some of them actually are properly folded or assembled, and some of them are not. Do you think you can use the heat capacity to decide which ones are the well-folded ones?
I'm sorry, I don't know, of course, because I do not know these things, but I hope. Heat capacity has a proven record of doing something in equilibrium to understand the structure of matter, to understand energy transitions. I would hope that it could open a window on aspects, at least, of biological functioning, which go beyond purely material aspects and energy levels, but that could reveal some aspects of measures of activity and what have you, organization, but that has to be seen. I hope it can grow, this field, but it's just very primarily, just very, it's in the progress, right? So I'm sorry, there's little results that I can say which are of sufficient sensation to make videos of.
Thank you anyway. Okay, we can thank another time the speaker.